Hi, I'm Kivisha Mohan. My metric number is B0820103227. I'm from Group 2. The title of our assignment is Analysis and Design of Digital Filter. Objective: to understand the type of digital filter, to study the design and analysis of digital filter, to explain the characteristic and design procedure of IR and FIR filter, to solve the problem by applying knowledge of design and analysis of digital filter. Introduction. There are two fundamental types of digital filter, finite impulse response FIR and infinite impulse response IIR. Both FIR and IIR different equation can be utilized to implement digital filters. This is achieved by choosing the appropriate coefficients. From implementation perspective, the IIR filter is more appropriate since the filter size is smaller compared to FIR filter to achieve similar frequency response. Unlike the IIR, FIR has linear phase that is necessary to prevent phase distortion. The purpose of filter is to accept certain type of signal and reject the others. The filter can be categorized by its frequency response. There are four types of filter: low pass filter, high pass filter, band stop filter, and band pass filter. This diagram shows low pass filter. The detailed frequency response characteristics are shown. These are the examples of frequency response of high pass filter, band stop filter, and band pass filter. The following session presented by my other groupmates. Thank you.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amin Muhammad. Okay, today I will present about my part, that is IR filter design. So, an IR filter design can be designed based on analog filter prototype by using the linear transformation as conversion from analog filter to digital filter. So, before we start the low pass filter, we need to follow the design procedure. So, the first one is we need to define the filter specification. That is cutoff frequency, sampling frequency, pass band frequency characteristic, transition characteristic, stop band characteristic, and filter order. Then next, we need to choose the analog filter prototype, and then we need to calculate the cutoff frequency of equivalent analog filter, where is epsilon the normalized cutoff frequency of the desired digital filter, where following the formula. Okay, and then we need to apply frequency scaling, Hs equal to Hs and S equal to S over ohm C. So then we need to derive the transfer function for the digital filter by making the substitution. Okay, and then verify the resulting frequency response of the digital filter by replacing in the transfer function Z. So what the goal of the IR filter design? So the goal is to design a causal stable different equation. So its magnitude frequency HED to the power of ohm approximate to H1 ED to the power of ohm. So the IR filter also have an order that is smaller. The order that means the number of delay on the system and also number of multiplies and need to compute to find and one output. It will cost less work, computational time, and power to compute output. In terms of delay, IR always save depression, which we can know that the frequency have a different delay. So the advantage and the disadvantage of infinite impulse. So the advantage is easy to design, easy to implement, and the disadvantage is that we know IIR is a non-linear, so it's quite difficult to design linear operation. And also we know that IR is non-stable, that is sometimes it will be non-stable and will make large number of coefficient. So for a classical IR filter, there is By-12, Chebyshev type 1 and type 2, elliptic and Bessel. That is all that approximate to the ideal brick wall filter in different way. So what is there is a various filter method, so I will only give the briefing about the analog prototype. Okay, so So the other prototype is using the poles and zeros of classical low-pass prototype filter and the continuous lattice domain. Okay, so they will obtain a digital filter through frequency transformation and filter description. Okay, there is also the direct design and the derived Butterworth design and also parametric modeling. So for IRR design filter, so here I have include the coding function. So as we know, IIR use Butterworth, so there is the coding for the Butterworth. And then I also include the Bessel analog ini, Chebyshev type 1, Chebyshev type 2 and elliptic coding. So that's all from me. Thank you very much.
Assalamualaikum, I am Muhammad Qazi Shukur. In this part, I will explain example of designing IR filtering from analog filter. So there are several methods that can be used for designing digital filter. The technique described are all best formatting an analog filter into digital filter. Use several methods to convert a digital filter. Widely used 4 methods to design analog filter into digital filter. So 4 methods they are: first one is approximation of derivatives, second one is impulse invariant transformation, third binomial transformation, and last one is match jet transformation technique. So in this presentation I will explain only IR filtering using binomial transform. So for binomial transformation have to fulfill 2 conditions, which is z axis in a S plane should map into the unit circle in the z plane. So thus there will be direct relationship between 2 frequency variable in the domain. So second, left half plane of the S plane should map into the inside of unit circle in the Z plane. So then we able to convert analog filter to stable digital filter. I will give one example of IR filtering using binomial transformation. So question already given digital bandpass and digital stop bandpass. So from here we calculate E is equal to 1 and lambda is equal to 4.8989. So first step, we have to find p-morphing analog frequency using this formula. So analog bandpass is 2 and analog stop bandpass is 4.828. So step 2, we have to find order of filtering. So for order of filtering finding, we have to use that formula. So formula we already know lambda and epsilon and stop bandpass and bandpass analog. So if we put the value, we will get 1.803. So step 3, round of n the next highest integer, which is n is equal to 2. Highest integer is 2. So if n is equal to 2, from table normalized butterfly filter is this. If n is equal to 3, it will be a different formula. So its formula is we take from normalized butterfly table. So we get already analog transformation. Next step 5, we have to calculate cutoff frequency. So we get cutoff is 2 radius per second, and step 6 is finding the transformation function, which is HAS above value of cutoff frequency by substitute this. So we get 4 divided by s square plus 2.828 second plus 4. So this is the final step, which is digital transform we get. So how we get, we already calculate this part. So we have to substitute the s here and here. So if we calculate, we will get digital transformation. So this is the final result. Question also will give like that directly the analog transformation and t value. So if like that, it's directly we can use the s value to here. SS. So if we put the S below here, if we calculate, we will get the digital transformation. So that's all about my part. Next part, FIR, will explain by my groupmate. Thank you.
Hello, my name is Muhammad Arfan bin Azhar, and the metric number is B081910059. I will explain about FIR filter. An FIR filter is inherently stable since the poles are always zero, and the frequency response is determined by the position of the zeros. There are several methods to design FIR filter, which is window method, frequency sampling method, Park-MC-Stirling algorithm, and least square approximation. The frequency response of a low-pass filter is defined such that HF equal to 1, where FC is the cutoff frequency, and the filter has an impulse response HT that continuous time and aperiodic. Sampling the impulse response Ht at the sampling frequency Fs result in the discrete time impulse response Hn. Due to the sampling, the spectrum of Hn, that is H exponent j to pi f, is periodic in frequency with period Fs that can be represented as a DTFT generation function. You can see the equation. This is the filter impulse response Hn that can be calculated by considering a period of spectrum. Fs per 2 is also known as the folding frequency. Suppose it is desired to design unity gain a low-pass FIR filter with a cutoff frequency Fc and a sampling frequency of Fs. The filter's impulse response is calculated as follows. You can see the calculation below. And the value of the function is divided by two conditions, where n is equal to 0, which is applied using L'Hospital rule, and other than n equal to 0 is applied to the function Hn.
Hey, my name is Samsu Pradimanikum, matrix number is B08191037. My part for this assignment is to do the example questions of finite impulse response as FIR. So example 1. A simple averaging filter is defined as yn is equals to 1 over n times x n minus 1 plus x n minus n. So A, let n equals to 4. Determine the transfer function, its zeros and poles. So solution is, with n equals to 4, we obtain the transfer function hz is equals to 1 over 4 times z to the power of -1 plus z to the power of -2 plus z to the power of -3 plus z to the power of -4. After normalization, this becomes hz is equals to 1 over 4 times z to the power of 3 plus z to the power of 2 plus z plus 1 divide z to the power of 4. There are 4 poles at 0, z equals to 0, and 3 zeros from the solution, z to the power of 3 plus z squared plus z plus 1 is equals to 1 minus z to the power of 4 divide 1 minus z is equals to 0. Therefore, the zeros must be such that z to the power of 4 is equals to 1 with the exclusion of z equals to 1. That is to say, z to the power of 4 is equals to e to the power of jk2 pi for k equals to 1, 2, 3, and therefore the zeros are z equals to j to the power of k with k equals to 1 to 3 and z equals to j, negative 1, negative j. So B, Determine a general form for zeros and poles for any n. The solution is, since the transfer function is of the form hz equals to 1 over n times 1 minus z to the power of n, divide z to the power of n times 1 minus z. The zeros are of the form z equals to e to the power of jk 2 pi over n, which is k equals to 1 and n equals to n minus 1. And the poles are all at z minus 0. So, C. By comparing yn and yn minus 1, determine a recursive implementation. Also the transfer function, together with its zeros and poles of the recursive implementation. Looking at this example, can we say that any recursive filter is IIR? So the solution is yn is equals to 1 over n times x times n minus 1 plus x n minus n, and yn minus 1 is equals to 1 over n times x n minus 2 plus x n minus n minus 1. By comparing yn and yn minus 1, we see that yn is equals to y n minus 1 plus 1 over n x n minus 1 minus 1 over n times x n minus n minus 1. This yields the transfer function hz is equals to 1 over n times z power of negative 1 minus z to the power of negative n minus 1 divide 1 minus z to the power of negative 1, which is equals to 1 over n times 1 over z, 1 minus z to the power of n divide z to the power of n times 1 minus z. So, for the second question, how to design a low-pass FIR with the following characteristics. Pass band 10 kHz, stop band 11 kHz with attenuation of 50 dB, sampling frequency 44 kHz. Determine the causal impulse response Hn and an expression for the phase within the passband. Solution. First, we have to determine the specification in the digital frequency domain. So the passband is equals to omega p equals to 2 pi 10 over 44, which is equals to 0.4545 pi rad. And stop band is equals to omega s is equals to 2 pi 11 over 44, which is equals to 0.5 pi rad. Therefore, we choose the passband of the ideal filter, which is omega c, which is equals to 1 over 2 times omega p plus omega s, which is equals to 21 over 44 pi equals to 0.477 pi. We need a Blackman window to satisfy the 50 dB attenuation in the stop band. With this window, the transition region has a width of 12p over n. Since we want a transition region, omega s minus omega p is equals to 2 pi over 44, we determine the filter length n as 2 pi over 44 less than 12 pi over n, which yields n cubed 12 times 22 is equals to 264. Therefore, we choose n equals to 265 and a shift L equals to 132. Finally, the impulse response is Hn is equals to Hd times n minus 132, which is W Blackman, which is equals to sine times 0.4545 pi times n minus 132, divide pi n times 132 W Blackman. Example 3. To obtain a finite impulse response Hdn, a rectangular window of length n equals to 9 is used. Compute the coefficients of the FIR filter with a linear phase characteristics ends with this infinite impulse response. So the solution is, for a linear phase filter Hdn is symmetric about n equals to 0 and the window is symmetric about n is equals to n minus 1 over 2, which is equals to 9 minus 1 over 2 equals to 4. So the formula used is Hn is equals to Hdn times omega n. Ho is equals to 0.323. H1 is equals to square root 3 over 2 pi. H2 is equals to square root 3 over 4 pi. H3 is equals to 0 and H4 is equals to negative square root 3 over 8 pi. That's all from my part. Thank you.
Hi sir, I am Nivika Ramadas and my metric number is B0819104770, and the conclusion for chapter 5 is digital filters are widely used in signal processing to remove or to keep certain parts of the signal. Digital filters are uniquely characterized by their frequency responses in the frequency domain, which is the discrete time Fourier transform of the time response. The principal time domain views where the difference equation and the impulse respond. The signal flow graph applies to either time or frequency domain signals. The frequency domain analyzes where data from the Z transform of the difference equation, yielding the transfer function, frequency response, amplitude response, phase response, pole zero analyze, or alternate realization. FI can provide exactly linear phase. FIR designs by window sinks or frequency sampling are simple. FI equilibrium designs allow better control of frequency breakpoints and of passband and stopband rebel. It is more complicated to implement. While IIR can provide similar magnitude response with fewer coefficients or lower side lobes for same number of coefficients. It can be designed by mapping analog filter to digital. The bilinear transformation is particularly flexible, but the frequency mapping must be taken into account. IIR more coefficients closer to desired response, and its wider transition band, less ripple in passband, more stopband attenuation. That's all from us, sir. Thank you.
That's caught in the crossfire.